All right, let's make a start. Good morning, good afternoon. Welcome to today's webinar. With me today, I'm Guy. I'm the product marketing manager for reverse engineering and inspection at Oqton. Today, I've got Scott and Andrew with me, subject matter experts on today's topic, inspection for additive manufacture. I'm not going to be saying much this webinar, just a couple of housekeeping things. If you've got questions, anything you want to ask about the topic that we're going to cover today, then feel free to use the pane in the GoToWebinar chat. We'll have a section 10-15 minutes at the end to discuss and go a little bit more in depth on any topics around Oqton, around inspection and additive manufacturing. Any questions that we can't get to today or need some slightly further explanation, then we will follow up afterwards. If you have signed up for this webinar, you will then have it available to watch on demand at any time. You'll receive an email probably 3 to 5 days after today to revisit and rewatch. So without further ado, I'll pass over to Andrew and Scott.
Thank you.
Hey, thanks, Guy. Hey, my name is Andrew McCune. I'm the Senior Regional Sales Manager for Oqton. Happy to have everyone join. Thank you, everyone, for taking time out of your day. I think it's going to be actually a really great time well spent for everyone here. I'm based out of the West Coast, a big fan of the company for many years. I consider myself a 3D scanning technology evangelist. That's me in a nutshell.
Yep, I'm Scott Green. Currently, I'm a corporate strategist and principal solution leader here at 3D Systems, and Oqton is a wholly owned subsidiary of 3D Systems. Before that, I was the director of software product management at 3D Systems for about 6 years, and I'm based in San Diego, California. And I'm really pleased to talk about the subject today because it's something that we have paid quite a lot of attention to in recent years, and it's an exciting part of the metrology field today. And anything else, Andrew, you want to say before we move on?
No, we've invited you, Scott, because you have just a wealth of information and been around in the industry for so long, strong ties to some of the things that we're going to talk about today. So just thank you again for joining us, and take it away, please.
No problem. Okay, so let's just talk a bit about 3D Systems. If you're more familiar with Oqton and not 3D, 3D is broken up into kind of two halves. Half is Healthcare Solutions Group, half is Industrial Solutions Group. And we have laser focus on segment-based approach in those areas. So for instance, semiconductor capital equipment or oil and gas or automotive, we have a corporate structure to dive deep into those applications and those segments to make sure that we're looking at like every possible thing that the customer would need and seeing that we have products and services and software to help satisfy the needs. So that's like materials, machines, things like that. So I sit on the industrial solution side, but healthcare is still a huge portion of our business, and everything is super important when it comes to the subject we're talking about today. 3D Systems is a global company. I'm in this little orange dot down here in San Diego, but we also have our major AIG manufacturing centers here in Littleton, Colorado, and in Leuven. And those places are pretty critical because they're just cranking out really high quality, heavily engineered direct metal parts. So that's really just centers of excellence for direct metal additive manufacturing, and a key component to the subject we're talking about today. To give you a bit of a overview on how we work, we're not just like a sales organization that pushes boxes. We have deep engineering expertise. So typically we go through about a 6-stage process to triage projects. And in here, additive inspection is involved at some stage, but it's just a piece of the entire chain. And that's kind of the major message that we're getting across today is additive manufacturing with quality requires process and metrology and the same kind of things that other manufacturing processes do. So typically we're going to explore and innovate. If you come to us with a problem, we're going to try to figure out how to make it better, how to optimize the part to improve performance or reduce downstream costs, assembly, and things like that. Go through a process of developing a way to make it. What machine, what material? Do we need to develop material for you? Do we need downstream machining suppliers or heat treat suppliers or coating suppliers? How do we create a work package to actually make a scalable manufacturing plan? And then we'll actually validate and produce. We can do short run production on metal parts and even plastics. And then typically our exit plan is to pass that off to a customer or to a third-party supplier to go ahead and scale. And that whole product of work is called tech transfer. That includes validation and inspection and various types of inspection validation.
Great. So that brings us to kind of the segue here. Why Scott, what in your experience, why are people using 3D scanning? Why is this so important in this type of world?
Yeah, okay, good question. So definitely this is a chart that you know our customers may have seen before that we've shown for quite some time. Is this product design and manufacturing life cycle. Metrology or scanning is in here at some point in time. You know, generally inspection is a part of making stuff. Okay, so I think we all have come here because we believe inspection is important, but we want to talk about why specifically is 3D scanning important. Now, if you're not 3D scanning a complex part, not like if you just have a machined part with high tolerances and a few features, it's going to make sense to do it differently. But if you have a part with any sort of complexity to it or value or engineering value to it, it's going to make sense to 3D scan. So the point of this visualization is to show that if you're not 3D scanning, you're really not seeing the full picture. So you can see what would happen if you took 1,000 CMM points and 9 million 3D scan points.
Yeah, that's a really good point. Like, for example, with traditional methods, right, whether it's manually, hand calipers, things like that, the question always comes down to, more data gives you a better representation of what's really going on, right? I mean, well, and I guess this is the next slide. If you're looking at a cylinder and you measure, 10 points, right? How cylindrical is it? How much confidence do you have in that versus getting a true picture? Same with flatness. If you measure 4 points, each point's 25% of your measurement versus getting a whole picture of what's going on.
Yeah, and Andrew, it's a great point. And if you walk away from that part, those are the measurements you have. So if you get full shape capture, you can walk away from that part and you got everything. At any point in time, you can adjust how you measure it. You could roll back from the edges, your tolerance. You can get total shape capture, so you have a digital copy. And I don't like using the word digital twin, but basically digital twin of the part.
Yeah.
So you got it forever. But if you do a CMM measurement or a manual measurement, when you walk away from the part, that's what you got. So with 3D scanning, you could get full shape capture, walk away from it, put it in the mail, ship it somewhere. Doesn't matter anymore. You've got it captured. So I think this is pretty clear. If you were to take CMM measurements at 1 point per second, and you need to take 9 million points with the 3D scanner to cover the same part, you just add that up, 9 million seconds to get the same amount of data. And I think you can calculate that out to be like a month of probing 1 point per second to get the same amount of data in a very short period of time. So very, very clear value proposition for 3D scanning. Now let's talk about additive manufacturing. So we're not just looking at like castings and like simple stuff that's actually pretty easy to measure with your CMM. It's even worse. It's even harder. The need for full shape capture is even more important, because when you decide to go to additive, it's generally not a good idea to just take a machined part or a cast part and say, hey, can you make this an additive better or cheaper?
Yeah, that's not
sometimes you. Yeah. I mean, sometimes you can, like if you're wasting 90% of your material into the machining process, you can actually get a cost savings if you 3D print it, because wasting 90% of a billet of titanium is expensive. So yes, you can actually, in some cases, print something in metal cheaper than you can machine it. But in almost all or most cases, the preponderance of cases, it's a tiny Venn diagram overlap of stuff that's compatible. So again, the values of additive manufacturing here is it enables high complexity. You get function first design, and that's a term we coined, which is when the designer is designing, they care about like, how do I make this function the best possible? And they're not like hampered by iteratively thinking, okay, I'll design that feature, but I can't make it. I'll design that feature, but I can't make it, so I have to change it. So it actually streamlines processes. We've seen, design process, this may seem really complex, but we've had to, even recently, like I had a webinar I had to give the other day where we didn't have full clearance to use the part because it was too close to something else. Additive actually unlocks like some easiness. We just redesigned it in an hour. I didn't have to think about like, is this super complex thing makeable? I knew it was makeable. It actually helped me design faster because those limits are off.
Right.
Yeah, and then the values of 3D scanning here are going to be kind of one-to-one with the values of additive manufacturing. You get total shape capture with high fidelity data collection, rapid data collection, and it's non-contact. So in the cases where you may have thin structures or surface finishes you cannot touch due to cleanliness requirements, it makes a lot of sense to use a non-contact method. And also, when you look at some of the new CT modalities there are to measure parts, you're capable of capturing stuff that optical measurements or even hand tool measurements are impossible to capture. And here's just a sampling of parts. I mean, here's a manifold and a bracket component consolidated. Here's another manifold and bracket component consolidated. These present superior fluid flow over traditional manufactured items. And this is a gas mixer with temperature control. It's got a gyroid pattern inside with a conformal cooling pattern that wraps around it. This is a lobed nozzle for a rocket engine. All these things, pretty unique parts, easier to scan than not. So I want to talk a bit about like expanding your definition of inspection. Inspection, typically in most people's minds is like in the lab with the CMM and hand tools and a lot of gauges and things like that. And inspection really occurs on more than just like precision machined parts. It makes sense to do something with quality and inspect it. If you're going to do something with quality, you need to inspect it. So a huge amount of inspection exists outside of this kind of traditional stereotype of inspection, and it's actually much bigger than you may think. What kind of methods are used in additive manufacturing? Again, I'd say, hand tools and destructive methods aren't great, but they are useful. Typically, at the bottom, you can see hand tools and destructive. A lot of times, you'll measure something with CT and with additive, with structured light or scan arms or something like that, and then still crack it in half and look inside it. Like these are layers of inspection that you need. But yeah, here's a sampling of non-contact scanners that we see and we support. And again, I'd see a lot of new CT modalities coming out, cheaper, better value propositions for X-ray CT, new scanning companies that are coming out, which make it much more accessible. And that's fantastic for additive manufacturing. It's no longer $500,000 proposition. It's more like maybe $30,000 a year on a lease. That's pretty cool.
Sure. Yeah. Or the point of entry, is opening up to the folks that otherwise would not be able to.
Yeah, absolutely.
Yeah. So I guess what are you seeing? Yeah, what are you seeing happening in the industry? I mean, how does all of this, affect the bottom line? I mean, how does this all tie into industry?
Yeah, it's important to take a look at like industry reports and market reports to verify your assumptions on like what's going on. And I really like this chart because, we're a big company that buys market reports sometimes. And this one is a 2016 picture, and I like it because it shows a prediction. In 2016, there's a prediction that by 2020, you're going to have this graph of applications where the certainty that 3D scanning will have a high impact is here. So high impact, high certainty that there's high impact. And the actual impact is very high. So the prediction in 2015, 2016 was that all this stuff in this blue area is going to have a high growth and high impact. Well, 2022, and we can look back and see, like, is this prediction correct? Well, if you've been paying attention to some of the things happening in LiDAR and BIM sim and forensics and law investigation, like whole companies and like billion-dollar industries have been developed on just 3D civil survey, moving beyond theodolites and total stations, insurance, law investigation, forensics, medical. I mean, medical, 3D scanning is critical to virtual surgical planning and patient-specific modeling. And that certainty is even, the impact seems low compared to what it actually has. It's actually quite high. And the one thing you see over here is 3D printing. And, the funny thing is that when you look at like the total applications of 3D scanning and 3D scanning in general, it's really about like 20 to 30% of the total use cases for 3D scanning is in modeling and reverse engineering. That's an easy one. Like I'm going to 3D scan something and then I'm going to make some changes or design an accessory that I'm going to 3D print it. Actually, like the 70% remaining of the puzzle is inspection. So you can make the logical leap and say, yes, I have seen stories about and marketing and use cases on 3D printing and 3D scanning and for modeling purposes. Well, there's a huge section of 3D scan use cases, which is actually just an inspection, and that's happening now. So I'd say happening later than they expected. We're in 2022, but the significant impact is actually coming now. Yeah, and generally, you also see, just from a scanner perspective, there's this like introduction, growth, and maturity curve where you're seeing stuff like industrial CT becoming much more accessible. I mean, in the last 2 or 3 years, there's probably a dozen new industrial CT scanning companies that they may not be able to scan the biggest stuff at the highest energy, but it really helps you with like tensile coupons, volume characterization, porosity, material development, things like that. All just like really assisted stuff where you can do CT scanning, material characterization on one side, and then you can do metrology right next to it. Yeah, so you're seeing, definitely in this like growth stage, you've still got like structured light scanners are getting better and better. You've got vision machines are becoming, again, a little bit better and better. They're starting to get pretty mature, but getting multi-sensor enabled, lower cost points, becoming more capable. Arms and laser trackers are getting pretty topped out, at least from my perspective, totally impartial 3D systems perspective. You start to see the innovation start to slow. I mean, one thing we are starting to see is more of a focus on multi-sensor articulated arms. So that's going to be super useful in the additive inspection industry is being able to switch between like high resolution scanner or super shiny scanner. Material flexibility is something that's direly needed in the articulated arm space for sure. And if we look at how this additive inspection and how measurement equipment is utilized in the industry, there's this typical pyramid of how stuff is made. You've got OEMs who own the designs at the top. You've got supply chains that service the OEMs. You're typically going to see at the OEM and tier one side more forward-looking kind of inspection ideals. And so they're more likely to adopt additive manufacturing quickly. They're more likely to adopt new standards quickly. Or when you get down to like the tier 2, tier 3 shops, like job shops, machine shops, things like that, they're going to go with like the cheap and easy standard thing. And that gets rolled up into assemblies.
Yeah, certainly. I definitely experienced with like aerospace, for example, the big OEMs are some of the early adopters. They're using not necessarily one technology, but they've got every tool in the toolbox for the right application. But then that opens up the door for the tier 1, where they're almost demanding that they be on the same page in tier 2 and tier 3, so forth. But yeah, this definitely resonates.
Yeah, absolutely. And again, like major aerospace companies are going to be pushing the envelope and the limits and trying new technologies, and then that helps actually in the market trickle down into those tier 2 shops for sure. So if you want to look at kind of what's happening in general, if you want to look at where metrology stuff is sold, and this all ties up into an assessment here after these couple charts, is you're seeing most metrology consumption is happening and software consumption is happening in automotive and aerospace. And this is an older chart, and I'd argue that actually aerospace is an even larger portion these days, because when you look at the explosion of private aerospace, just space access industry, because you've got like payload, which is like the satellite, and then you've got access, which is the rocket that puts it there. Companies like Launcher and SpaceX and Ursa Major, and the list goes on. Relativity Space, these bunches of companies that are focusing on new technologies, as well as that opens up the payload capability too. So if the cost to put something in orbit starts to go down, then it gets more accessible for someone to actually pay to put something up. So when I say aerospace, I'm not just talking about 777. I'm talking rockets and space access. So these guys are definitely
for sure.
buying.
I mean, when you're looking at sending something out into space, here every ounce, it is costing. There's a significant amount associated with that. So when it comes to lightweighting, which is big benefit of additive manufacturing, that all ties in, and that's going to trickle down. And how do you measure a part like that?
Yeah, absolutely. I mean, these aerospace guys are definitely huge adopters of additive manufacturing, just simply because of the strength to weight ratio advantage of topology optimized structures,
right,
and lightweight materials. Yeah. So those companies are starting with additive manufacturing, like in the charter. Like, we are starting a company to additively manufacture rocket components. Like that's what they do. So then other contributors here are going to be oil and gas, power gen, healthcare, and consumer products. But largely we're seeing those major concentrations in those two areas. Now, if you want to ask and look at how are people using additive manufacturing, and we're going to cross all these together and make some assumptions, generally you're seeing over a trend over the years where functional prototypes used to consume, 5 or 6 years ago, a lot of the graph here. But the end use part chart is growing faster, which means that, engineered plastic materials are good enough and long-term stable enough that they're good enough to be end use parts. So we can 3D print stuff that will last for 15 years and outlast injection molded parts in many cases. That's a new trend, is production quality plastic materials. But metals, of course, the expansion of metals, the maturity of laser powder bed fusion, and even the new entrants into the metals market are making more and more end-use parts more feasible. Oh no, it's not showing me my country breakdown. There we go. So then if you look at the regional growth breakdown, it's not showing me how I wanted to show it, but it's okay. Generally, you're seeing the Americas and EMEA leading the growth breakdown of additive manufacturing, with China and Japan and Korea kind of trailing. So the Americas and EMEA, the European countries, consuming the most amount of additive equipment, with China and Japan and Korea trailing those. So what this all means when you cross it over with each other is that the industries we're seeing most interested in advanced manufacturing technology and most interested in metrology software and most interested in additive inspection are definitely across North America and Europe, consuming the most amount of scanning equipment, consuming the most amount of production additive manufacturing equipment for end-use parts. And this is where most of the opportunity and action that we're seeing is. And other key contributors are definitely in the virtual surgical planning and patient-specific implant development side. That, as we'll see in the laser chart has become, they had a good head start on everybody else. And, virtual surgical planning relies on CT and MRI data and is naturally been using direct metal printing and additive for quite some time. And there's very well-developed methodologies for inspection there. And we also see other segments that are key contributors. When you look at some, again, key takeaways from market reports is 55% of machine sales cases are indicating that quality is either critical or generally important. That is 10 times higher than it was in 2009 for additive manufacturing. And some of the simple quotes from customers: process control and inspection capability is a critical need going forward. And in 2018, as a service bureau, we saw customers looking for quality services rather than just machine capacity. So the industry accumulation is there. All signs point to that this is an urgent need and thing that if you're not paying attention to, you should. And there's definitely many publications that we've had and are been in the market about this.
Yeah, so there's no doubt that the industry is growing, the applications are maturing. I mean, I think you and I got back in the industry, well over a decade ago, when it was still considered rapid prototyping before we really saw, the adoption of actually manufacturing using these technologies, getting into metals and things like that. But I mean, where do you see the scan-based inspection now? Because it has been traditionally used for, the CNC parts of the world, the stampings and whatnot, the mature technologies when it comes to manufacturing. Where do you see that in additive?
Yeah, it's an important point to communicate to our readers, our listeners. So a good way to look at like a maturity gauge is, you can take a matrix where you've got like all possible manufacturing technology in your rows, you've got all possible segments in your columns. You just make an assessment. In the automotive industry, they use machine parts, castings, sheet metal, plastic parts. We know for a fact, we work with those suppliers, like we know that inspection is a critical part of those industries. So you can kind of expand that out. And, the one outlier here is in heavy industry, you don't see that many injection molded parts, so they're not that critical. That one, just not an amazing fit. It's more heavy industry, it's heavy stuff. But if you look at the additive manufacturing, this is a new entrant, like a serious entrant to the production space. So you got to add a new column for it. And if you look across the board, I'd say that the gauge of the maturity for additive inspection in the industry is directly related to the amount of time that additive has been applied in that industry. And in the healthcare side, over 10, close to even 15 years, there have been companies that have been looking at even just cranial patch, right? Cranial patch is one of the first virtual surgical planning processes that were used for patient-specific implants. That involves CT scanning, that involves a single part that is for a single person, and that involves inspection on that part, only that one part, to make sure that it fits correctly. So inspection is quite mature when it comes to additive manufacturing for healthcare. But when you look across the board, automotive and aerospace are in this kind of developing stage, heavy industry in the developing stage, and we're going to see these slowly turn green over some time. And yeah, if you're on this call and you're a listener today, you may be interested in like just one of these, like, hey, you only make machine parts, but I want to kind of give you an idea of what traditional inspection looks like and just flip through some examples. So here's a casting that's machined, that's inspected. This is a common use case. So for traditional manufacturing, quite mature. Again, traditional manufacturing of pumps and turbo balloons and impellers, all quite mature. And, again, what additive manufacturing is doing is taking, in many cases, some of these legacy parts or things done the old way that are already being inspected. If you're not making a brand new part that's never been made, and you're taking a part that has been made a different way, and you're transitioning it to additive with new functional value. Again, I said it's not a good idea to take an old part and just make it again an additive. But if you're reconsidering something like an impeller and you want to make that with additive, and you have some functional value, whether it's like integrated cooling or lighter weight or something like that, and you were inspecting the old thing, you're going to be inspecting the brand new thing. And every one of these applications that I've shown could easily be additive applications too. So what I'm showing you are examples of traditional manufacturing where inspection is already a key part of the process of producing that part, and where additive manufacturing is playing at creating new parts.
Yeah, that's interesting. Goes back to the, just because like you could 3D print or additive manufacture a lot of different things, but it doesn't always make sense, right? I mean, you've got to look at, what's important. Are you making just one? What's the cost ratio? How does that compare? How the performance of the part, things like that. So I'd also ask the question, same for the inspection side, like when does it make sense to inspect at all? And when does it make sense to use a scanner versus just sticking with your traditional tools?
Yeah, good point. And the last thing we have here is an example of something very real. It's a traditionally die cast or sand casting part for an automotive application that we transitioned to additive manufacturing just because the volume was low and they didn't want to make tools. So let's kind of enter into the subject of when does it make sense actually to inspect. So this is a super simple chart I created to just very clearly indicate that more often than not, it makes sense to produce an additive part with quality. Now, what are the obvious cases where it doesn't make really a lot of sense to use a complex inspection method? Well, when you have a low volume part that has low value, right? Low cost, cheap, short run part. It's going to make sense for you to either not inspect it at all or just do some simple measurements because typically it's not highly engineered if it's low value. But in almost all other cases, if you're producing something with additive, if the customer is giving you money to make something for them and it has value to them, it's going to make sense for you to do it with quality. And that's, just a very simple vanilla stat you can give that's very obvious and backed up with data is companies who are perceived to make higher quality products do better than companies who are perceived to make lower quality products.
Right. Yeah.
Very, very clear assumption, and it's absolutely true. So I want to also just again reiterate this point from earlier, which is that in additive manufacturing, quality and accuracy are 10 times or more important today than they were in 2009 or in the early 2000s. So I just want to hammer on that.
I'm looking at the data and I'm thinking that's actually probably even more so today, right? With the cost of material goods, logistics involved, that you get it right the first time, right? Or
and Andrew, it's even more critical because through COVID and all the supply chain reorganization that happened, we saw these stats are pre-COVID. So during COVID, we saw major supplier consolidation and people looking at different ways to manufacture stuff. We've experienced that in the semiconductor capital equipment industry. Is okay. I had 5 suppliers who made this thing. I know if I go to additive, I get into one supplier because it's component consolidated. And then, I need to make sure there's quality there. So it actually helps transition people to additive in saying I need to secure my supply chain and go from 5 suppliers and an integrator down to 1. So it's even more
thing instead of a part, a widget, or whatever, instead of having 5 pieces that it's combined from a from an assembly to a single part.
Yeah. So instead of me as a supplier going and getting one component from you and one component from your neighbor and one component from his neighbor, and then paying the other neighbor to put it together, I'm just paying you to make it all in one. And because of that, you're adopting new technologies, and they inspect it the last time the old way, and they're expecting quality the new way too. So, and that actually is
a 5 reports, and getting them all integrated into one. And if it doesn't fit, who are you pointing the finger at, right?
Yeah, it's a nightmare from a supply chain perspective. I mean, it really makes supplier sourcers' job easier to reduce supply chain risk.
Right.
That's another thing that additive helps do. And I think for a long time, marketing and additive has always just like focused on supply chain risk, streamline your supply chain. Well, that's one aspect of it, but in the process of streamlining your supply chain, we're adding significant functional value to like better heating, better performance, better cooling, better product performance. So, that's another consideration to have. And one thing when you're talking about single individual components that are made, everyone, if you're making stuff today, you're familiar with the concept of first article inspection. And I like to use this graph because it shows the amount of data you need from a manufacturing process versus the time that you're making that thing. So in the early stage kind of NPI, new product introduction process, you're gathering as much data as possible. Like, why is that failing? Why is that not working? Before you even ship to the customer. And then you hit the first article point, and then, okay, you're doing customer shipments, and then you slow down your sample size. You measure 10 features, then 5 features, then 2 features. You just keep going. Now, that's all enabled by like hundreds and sometimes thousands of years of history in manufacturing. Casting is like 5,000 years old, okay? Like, no one's taking a job and trying to figure out how to cast things anymore. They built on so much history of actually learning how to make that. So, traditional manufacturing has different advantages when it comes to quality. Now, let's look at what it looks like for additive. For additive, even companies with a small number of machines or a large number of machines, when they get a new project, it's a very serious thing to figure out how to make it right. Simulation is involved to help reduce the amount of information gathered by actual practical printing and measurement. And iterative measurement is included too. So on the metal side, you've got like printing, you've got heat treating, you've got support removal, plate removal, EDM, machining, finishing, like 5 stages where that part can change the entire way throughout it. So additive inspection is pretty critical in this early stage to characterize, okay, who's got the problem in this series? Is it heat treat, or did something happen when I machined? Did it spring up somehow like a potato chip? Like where did it happen? So in this like kind of unknown stages right now, while additive is still maturing into something like machining in 10 or 20 years, a lot of information is needed for almost every project.
Yeah, so it's not just getting a report of what does the part look like, but it's actually facilitating and trying to understand where in the process, did something occur. I'm forgetting the term used in manufacturing, but you're almost like almost kind of reverse engineering the problem, like trying to figure out like where did it start so that I can identify, try to fix the issue before I go make another 1,000 of these widgets.
Yeah, or do another turn on a print and try something sketchy or risky on a print to try to compensate or fix a problem when it didn't even happen there, right? You're just wasting time and money. Metal prints are expensive, like from a cost of goods and operation perspective, like billet is relatively cheap. Machine tool operators are relatively cheap. Machine tools are also relatively cheap. So you want to be very careful and use the tool when you need it. And again, this is just a clearer view that typically, the highest contribution that inspection software and scanning can have is actually like to the left of the first article inspection, where like to the right is more like traditional inspection. So, okay, first article and beyond is really where traditional inspection is. So what are you actually inspecting? Let's talk about that. Generally, a part is generally an additive part that comes off a machine that's not a result of a controlled process. Maybe the first time you printed it, I have to recognize, again, I work for 3D systems, so we have one set of knowledge, but then, I used to work on the software side, so I have exposure to all different types of 3D printers, because I know that there's other systems that are open material systems that maybe don't have as good a process locked in for parameters. So But many times the customer has some experimentation to do, especially if they're running their own material and they don't have fully developed parameter sets. So typically you're going to have a part that comes out that has some combination of these three types of errors, and it kind of is like an alligator mouth of like worst possible stuff to smallest possible thing. Where generally you're going to have a high contribution to error in just like, is the part the right shape? Like, is it warped?
Right.
Is it correctly? Is it twisted in a way I can predict? And you've got like no hope of doing traditional inspection on something unless that's under control and your process is under control. So that's a key contributor to process-based error. And then you've got kind of finer and finer grained stuff that we'll talk about in the next slide. But generally, you may wonder, okay, what about porosity? Yeah, porosity is like still a consideration, even more so for some metal printers than other. Again, this gets down to like the manufacturer to manufacturer of printer. But, in printers where porosity is not as much of a problem, that can be considered controlled by using inspection by proxy. And inspection by proxy is a concept where you may print a chunk of the part and CT scan it, and then also print a tensile bar or a cube next to it and correlate the two and say, okay, I can predict that the porosity shown in the cube or the bar is similar to the porosity in the part chunk I printed. So therefore, I can say I can print the full part with confidence that that cube is representative of the quality of the part over there. So inspection by proxy is like, I print something easily measurable next to it and I check that. It's like checking your tool almost instead of the part that comes out of it. So, in some manufacturers, if you're really cranking through a print using large layer thickness and a lot of power, you may have a lot of inclusions that you need to continuously check. It's just a printer to printer thing. But I like to think of this as like, what moves the needle the most in getting good quality versus what moves the needle the least. This kind of 90-10 rule. 90% of the work can be done in 10% of the time with coarse grain changes and adjustments to get the part into shape. And then sometimes your last 90% of the effort is in that 10% of quality, which is this kind of finer feature adjustments and surface deviation and finishing and things like that. So you can kind of whack a lot of a process problem with parameters and process itself. And that's pretty key. Now, one thing that may be coming into mind, and a lot of people commonly say, is like, how come I can't just like counter compensate the part? Like, why don't I just twist it the opposite way or like make it smaller and so that'll work? And that's actually a pretty reasonable thing to suggest, but it's pretty useless unless you have a well-controlled process. So if you can't be sure that repeatably the same thing is coming out of your printer, and if you can't be sure that you understand the process that is making it, then counter compensation is not going to help you at all. And also, we know from experience that large counter compensations are extremely unpredictable. Small counter compensations are actually more successful. So the suggestion from an additive process and inspection perspective is try to solve as much as you can with parameters and process. And then if you just got to get that last little bit of error out, then you go to counter compensation or stock adding and machining, and then you're kind of remediation, root cause remediation. But there's a lot that can be done to compensate errors or to correct or remediate errors by just simple orientation, build style parameters, supporting strategies. Those are things that typically you're going to need to develop. It's not good enough to just bring a part in and blast it with supports and say, okay, that's great, because that has a direct connection to part quality and finishing time and things like that. So it's always a careful balance in a production setting to use the minimum amount of support you need so that you can not only reduce the amount of work after it comes off the machine, but also keep quality static. So what can you do for root cause correction? I mean, additive is an inherently digital process, which is pretty awesome. I mean, data is absolutely everywhere. With the kind of adoption of Industry 4.0 and companies, such as Oqton, you guys, and other companies in the market, this kind of shop floor management, industrial IoT, fleet management, data logging, all that's really important because you can connect things you see back to the environment that it's working in pretty easily. With the machine shop or casting shop, it's pretty dynamic, right? No one's capturing like ambient air temperature inside of a machine tool and correlating an error back to it. Like, that's just not common, right? So the advantage you have with additive is data is absolutely everywhere. You've got slice data, you've got digital build files, you've got build vision inspection, you've got laser pool, melt pool inspection, you've got all this great data that you can use to root cause correct.
There, Mike's up. Hey, so can you give some examples of what are you seeing in the field now? What's happening?
Yeah, for sure. Let's do that. So one thing that I'm super close to is, I sit here in the San Diego office where we've got a good chunk of dental guys, and I know for a fact, I've been a part of for quite a while process engineering on dental printers, assisting those guys doing process engineering. So for those cases where you have new machines and new materials or new support structure strategies, try to save the customer time and money, 10% reduction in supports with this new software release. Well, you got to check whether the part quality is going to change when you automatically take away 10% of the supports. Or if you have a new material, you need to check it against all of your supporting strategies and all of your slicing strategies to make sure, okay, am I getting what I expect to get out of this printer? So process engineering on the DLP side and the resident DLP side is something that is not obvious enough, I think, for people. I think if you're developing new materials or new applications, high production applications where quality is required, it makes sense to just verify that your supporting strategy, orientation, and post-processing strategy is locked in. There's no variation. So this is a common use case in the dental market that I don't think people are really aware of. Here's a good CT example. This is a wax investment casting pattern. Now, in this case, what we're actually doing is looking to see is in this jetting application, you were jetting soluble wax on top of castable wax, and we're trying to prove, can we build internal channels and pin tile nozzles inside this wax pattern? And I know we can build it, but the most important thing is, can I clean it out? So this is really similar to like trapped powder analysis in the powder space. Is in my oven and soluble fluid post-processing process, are these channels clear? Like, are they completely clear of support wax? And if they are, then fantastic, it's a proven technology. Again, this is process engineering. Can I make this part with internal passageways and nozzles, and can I clean that part out? You can't see it. You can destructively analyze it, but any single cross-section you might take out of it might be a false positive or negative. So total shape capture is pretty critical. Here's another great example, again, like spinal cages. This is kind of a generalized spinal cage-like thing. Lattice inspection is something that is very real. Color mapping a lattice and making sure that the nodes and struts are in the right place is kind of ridiculous. But most importantly, what you want to do is figure out, is the lattice in the right place? Is it where you need it? Is there any lattice where you don't want it? That kind of thing is actually pretty critical. And on those mating surfaces is the functional feature interacting with the actual healthcare purpose and application. Also, you can take a look at examples like build volume inspection. There's so many cases where if you independently measure a part, any single part in this lot, for instance, here's a great example. If I pick just part 1 and part 3 and I measure them by themselves and I look at them, I'm going to say, what the hell's going on here? Like they look completely different. What's wrong? But if you really look at it in build scope, you can actually see global build trends. That helps you analyze if you have a production build volume, and your parts are varying in some way, you go back to the process, which is the build volume, and you try to certify this collection of parts and serial numbers on this machine and this material is functioning the way you need to. And it's actually a good root cause analysis tool when you have parts that are non-uniform and divergent.
So that would be an important to measure more than just one part. Because if you measure just one part on a build and made the assumption they're all good, that may not necessarily be true. Because we haven't gotten to that,
right.
That peak in that chart that you had showed earlier where we've adopted and we're confident in our process.
Right. Yeah, again, if you pick any one of these parts, they're going to look very different from each other. And if you measure all 4 of them independently as an inspector or a quality guy, if you're thinking in traditional inspection terms, you're going to have no idea what to do with that data other than saying these are all junk, right? So you got to go back up the chain and look at it in scope, the proper context. Here's another really good tangible example that we talked about several times is that, foundries know their stuff pretty well, but they've also gotten to the point where they've generalized rules to make it simpler. They know for, a block of aluminum that's 3 inches by 2 inches, you're roughly going to want to apply the scale factor standard. If you come, they're going to say, 2.1 and 1.8. That's what you got to do. Well, we had a suspicion that we could actually do even better than that. And through a couple tuning loops of printing scale compensated parts, not warp corrected parts, but scale compensated parts, because the casting process adds, if you look at this, I'm printing, I'm post-processing, I'm then coating in a slurry, I'm burning out the wax, then I'm investing metal into that pattern. There's so much heat involved everywhere. that by the time you get to the casting process, there's an inherent shrink and expansion, and also stuff like shut off that can happen in certain small feature areas. So we're actually can prove compensation through a second process just by scale, since casting is adding scale uncertainty. You can measure that scale uncertainty and then back compensate onto your printed pattern. And what we're able to do is actually double the precision and accuracy of the casting process by just doing one measurement analysis, one measurement loop.
Wow.
And we're coming close to wrapping up, and what I wanted to do is give you an example of further reading here, which is I have an even more detailed analysis that we did several years ago on the 3D Systems website in conjunction with scanner vendor, a scanner partner of ours. This is a very similar case study to the casting pattern compensation process. It's a more detailed look at what we did to understand the values of improving our process. We ended up saving material time and print time by printing lighter weight casting patterns and proving that they were more shelf stable. So over a period of time, they actually stayed in the right shape as opposed to printing a solid pattern, which was heavier and actually drooped and sagged. The more it sat on a table, it actually was going like this. So we were able to print a pattern that was a different composition of infill and different internal geometry, which allowed it to stay more shelf stable in the process of getting to the next downstream process. And we also compensated scale error to get a perfect pattern and a perfect result.
It's awesome. So what's the future look like? What's next?
Yeah. So things are exciting right now, but I think that in the upcoming years, you're going to see this chart be surrounded by different tools. I think generally Oqton is doing a fantastic job of developing a baseline platform for all of this stuff to sit on top of, so that all that data can be collected in a common package. And then another super interesting thing that's happening now is closer integration between build prep and inspection. And right now with Oqton software, there's tools in place to do this, and that's through visual scripting. I think as visual scripting continues to grow, it's going to help connect 3D Expert and 3D Sprint and Control X and make a tighter feedback loop so that you can actually bring projects in and get root cause correction back into the build prep. That's something that is going to be critical to streamlining, managing all that data, because I mentioned it's inherently digital process. You got data everywhere. You don't want to be managing it yourself. So systems in place to be able to manage that automatically is pretty key. And I'd say also that, the role of the additive engineer today is kind of like this multi-hatted guy where he's like not only the designer, but also many times the machine operator or programmer, and then the operator, and then he pulls the thing out of the build and sends it to the people who may be responsible for depattering and finishing. And if you look at an analogy of that role to traditional inspection, those are all very different people. So as the industry matures, that person now who may be wearing many hats is going to turn into a different role, or you will have completely different designers as they mature into better additive design, and machine tool programmers or additive machine programmers, and then also just separated operator roles that just manage the machine, and then separated finishing roles. So that'll actually diverge and expand into different personnel. But the role of the inspector in the quality lab is really never going to change. I mean, this shouldn't strike fear into the hearts of the inspector that goes to work every day and produces quality reports. And what it does do is offer the opportunity for expansion and doing some new, unique things. So the software tools will change, but I think it's a requirement that better collaboration in this transitory period until there's full maturity, the communication and collaboration and data package storage so that everyone can have visibility on what's going on is important. So more tools are going to be needed to be able to share that data and collaborate as these functions separate. And then I'd also say that, CT is becoming a little more ubiquitous, which is going to really help drive some of the kind of trust and comfort people have in the additive manufacturing process. And as I mentioned before, there's definitely a shift in the manufacturing environment to more digital processes and data storage and total data package collection and traceability of like machine and material lot size and source and batch and material test batch all together. So there's a package of things for this part made on this machine with this material from this batch from this supplier that was tested with these parameters. So if anybody has any questions, like an aerospace company, it's all there. And stuff like Oqton MOS is clearly a way to do that.
Yeah. Thank you, Scott. That's
no
a wealth
problem.
of information. We covered a lot today. Are there any like 2 or 3 takeaways that you think that the folks should, at the end of today that they should have, really, like, how would you summarize what we discussed today? Like, what do you think you want our viewers to take home?
Yeah, I think I can give you a homework assignment, okay, which is if you're using additive today or have used it frequently and you've been unsatisfied with what you got, okay, whether you've always, maybe there was a head scratcher problem that you had, you printed something or you tested additive and you got parts and you weren't quite sure what happened or whether they were right, and you have access to scanning tools or you want to have access to scanning tools, start a project. Just go back and investigate to see if you can add further understanding, because sometimes what we see is customers who are looking to adopt additive and parts are made and samples are made and they kind of use them and look at them and they go, not quite right, or I need a change and I don't understand it. It must not be ready yet, and they put it aside. I'd say that's actually the wrong thing to do. What you need to do is go deeper investigation. Think about the ways that you interact with your casting and machining suppliers. You actually check those parts. You actually require first articles. You actually require quality data from them. So I'd say I'd give you some homework to go back and think about those cases where you did use additive and something wasn't quite right, and go back and investigate it. Because typically, if you're going to engage with a service provider on a very short period of time and say, hey, I need this part really fast, they're going to go fast. That's what you asked them for. Okay. So you got to ask them also, like, is this part right? And I'd also ask you that in the future, if you do go back to a service provider and ask for additive services you expect or to be quality, give them the time to do it right for you as opposed to an urgent matter. So an urgent matter, you're going to get urgent results. You want something done with high quality, treated like a serious manufacturing process and require inspection data.
Right on. We've got a few more minutes. If there's any chats, or sorry, any questions, feel free to add them into the chat window. I'm not sure if Guy has access to see those.
So Andrew, for you, when you're out in the field over your career, have you personally seen more customers using additive, more machines popping up, and they kind of popped up out of nowhere five or 6 years ago, and then they're transitioning from like toys to like more serious stuff. Like, what's your takeaway on the customers?
Yeah, I mean, I remember back in college working for a partner, there was this question of, is there still going to be this production grade, as we're going to see more hobbyist printers, like what's going to happen to the market? But surprisingly, both happen, right? We still see these very high-end great production systems that haven't gone away. And actually, having into the last Rapid show, I was amazed at how many more players I've seen come into the market with all different types of materials, more metals, more polymers, more, we're seeing things in shoes being adopted, right? And the soles, and all these applications that were just not possible. And that with that comes, additional processes that need to be in place and created using technology that wasn't required before. I mean, there's porosity things that we're seeing that affect performance. There's how do you do that quickly, and accurately, whereas before, if it was a traditional method that was widely already adopted and proven, you could run with, maybe doing a sampling and after first article, and then from there, have a higher degree of confidence.
You actually brought up a great point, which is, if you go to a specific machine tool show, you're going to like IMTS in the machine tool alley. Okay, I don't mean to disparage any of our machine tool friends, but I mean, kind of the same as last time, right? And like kind of the same as the time before that. Like, these more mature industries aren't changing as much. It's not requiring much investigation. It's more like you can kind of make a choice on like what color it is and how nice the sales guy was to you, like it was a Chevy or something like that,
Right.
But in the additive space, I mean, you've got like dozens of like incredible, cool technological advancements happening every year, and that's in materials and speed and performance and productivity. And some people might find their right fit, but at the same time, you have to recognize that it's proven, but it doesn't have like hundreds of years of history behind it. So it's important to understand and be more of a participant in the process, which might be weird for some manufacturers because they're so used to like just farming stuff out and accepting it or trusting a machine tool. Like this is cutting edge stuff, right? And it's in the stuff, there is mature additive technologies that are becoming even more mature, but there's even like more advanced high tech stuff that's less mature. And if it fits you and it's the final solution you've been looking for making the set of parts in a certain way, then get involved and participate and understand how it's going. And that's how you become an early adopter. You don't just wait for it to be mature and then buy it. You got to get involved and understand it and do it.
Yeah, there's a lot more questions. We're still on, frontier of many things. I remember working for a service provider. It's like, well, we could print this one way or print another way. The other way is going to take twice as long, but the product is going to come out, with a higher, a greater performance, right? But that might require more support structures or things like that. And there's ways we can lightweight that may be good, that might not be so good. But the result also is going to affect how we inspect the part, right? Maybe we need to look at layer thickness and power separation, things like that. Traditional methods of inspection just won't cut it. But yeah, I mean, thank you so much, Scott, for joining. The folks that are on the line, I mean, if you have any other questions, we definitely would love to field those and take those, and we can set up additional talks with those that are on the line.
Yeah, you can definitely use your forms at Oqton.com or 3dsystems.com. Look Andrew or I up on LinkedIn. We're happy to direct you to the right place or answer questions.